Good afternoon, everyone. Hope you all are ready for the weekend coming up. It's holiday weekend, right? So we will not have class on Monday. And as of today, I have heard nothing about whether or not we're actually going to be on campus next week or not. I was sent an email by the chair of the department saying that the college was supposed to announce today sometime, and I haven't received anything unless it just happened. So please pay attention to your Canvas email. As soon as I know something, I'll let you all know. As far as as far as I've been told, we're meeting on the 8th on campus. So in the event that we actually do, just go to Canvas and go to the course. If you're unsure of where we are supposed to meet, right? We're supposed to meet on campus in Juniper Hall, room 315. Our class goes from 1 to 2:40. So I'm willing to bet a lot of money that we're not going to meet, but I don't know. I've been surprised before. So any questions about that? Okay, last class we had started doing functions and domains and difference quotient. We just got into this. Also, the solving equations homework, I did post the video solution to that, and I sent an email to everyone letting you know like where you can get to it and that it was available. So, all right. Notes, let's get into today's material. So this is a continuation from last time. This is just making sure that we are all very comfortable evaluating functions. So if you're given a function and asked to evaluate at different values, can you do it? So we're going to just continue with another example. This one's a little different. Last time I gave you a polynomial function. F of x was 3x squared plus 2x minus 2, and then I asked you to evaluate that function at several different places right here. And so let's start with this one here. So we're given the function f of x is 4x plus 3 over 5x minus 8. And we're going to start doing some of these. I'm going to do the first few myself because these go pretty quick. Part A, all we want to do is plug 0 into the function. So just replace all of our x's with zeros. And of course, the 4 times 0 and the 5 times 0, that gives you 0. So all you're left with is the 3 on top and the -8 on the bottom. And that's it, we're done. So we plugged in a number and it spit out a number. Part B, we plug in 1. So we get 4 times 1 plus 3 over 5 times 1 plus 8, or sorry, minus 8. And just make sure we do the operations in the correct order. So do the multiplication first and then add the 3, so you should get 7. And 5 times 1 is 5, take away 8, you get -3. So that's what we get when we plug in 1. And let's see, we'll plug in -1. We'll get 4 times -1 plus 3, and then 5 times -1, and then minus 8. So up top, we get -4 plus 3, which is -1. And on the bottom, we get -5. Take away 8 more, we should be at -13. And that will be positive 1 over 13 because a negative divided by negative is positive. So all of what I'm doing here should be pretty okay for you, just plugging numbers into a function. Things don't get complicated until you get to the next few problems where you're not plugging in a number, you're plugging in variable expressions. So for part D, I'm going to change colors because that's kind of like where things are going to change here. So if we plug in -x, all we're doing is replacing all the x's with -x's. And since we're plugging a variable in, we should expect that our answer will include variables. So I multiply 4 times -x, which gives me -4x, then I add 3. Then on the bottom, I multiply 5 and negative x, get negative 5x, and then subtract 8. And there's nothing else I can do to this. I'm pretty much done at that point, right? So variable expression went in, variable expression comes out. For E, the difference between part D and part E is in part D, we're replacing x with negative x. But in part E, all we're doing is making the function that we're given, we're making it negative. So that means I'm just taking a negative sign and throwing it in front of the function. And that is it. Okay, a negative in front of the function. Now, you could, if you wanted to, put the negative on top, meaning you have to distribute it through the top. And I talked about this in a previous class. When you have a negative on a fraction, you can leave it out front, you can put it up top, or you can put it on the bottom. So I could have decided to move that negative to the bottom, leave the top alone, and make it negative 5x plus 8. So all three of these are equivalent. Are there any questions so far? Okay, how about F? F is where things start getting interesting. So when I have F, I'm going to try and plug x plus 2 into the function. And that means I'm replacing, right? Everywhere I see an x gets replaced with the entire expression x plus 2, which means when I plug it in, I'm going to need to put it in parentheses. So 4 times x plus 2 and plus 3, and then 5 times x plus 2, and then minus 8. One of the common mistakes that I see, and this may seem like, how could anyone ever do that? But I do see this. Some students will think that this means, oh, just take the original function and add 2. Right? That's not what this means, right? We're not just taking the original f function and adding 2 to it, right? We are replacing the x with the x plus 2. So I need to finish this up. I'm not done. I'm going to distribute the 4 through. So get 4x plus 8 plus 3, and then on the bottom, 5x plus 10 minus 8. And then I can combine some things together. 4x plus 11 on top, and 5x, what's that, plus 2? Let me erase this. Don't need that. Okay, we still good? Questions on
One
that?
question about E.
Yes.
Is there a reason why we have 4x plus 3 as the answer and not 4x minus 3? Negative 4x minus 3?
Wait, on E?
Yeah, for the final answer.
Right here.
Because didn't we flip all the signs? So why did the signs on the numerator flip back for the answer?
Okay, so this goes back to, all right.
Oh, never
so,
mind. I see.
You sure?
Yep.
I'm going to write it down anyway. If you ever have a fraction with a negative in front, you can move the negative to the top and leave the bottom one alone, or you can leave the top one, don't touch the top one, and put the negative on the bottom. So negative signs, they float, okay? They either float out front, or they move up to the top, or they move down to the bottom. What you don't do is the negative goes to both the top and bottom at the same time. Because if you do that, then you've actually made it a positive, right? Because a negative over negative would be positive. So in the first one, I just left the negative out in front of the function. The second one, I decided to move the negative up top, which changed the signs on the top only. And on the last one, I decided to take the negative and push it to the bottom, which would have been change the signs on the bottom. Any other questions? Okay, I'm gonna copy. Oops, I'm gonna copy this because I'm gonna have to scroll down. So put it right here. So the next thing we want to do for G is we want to find out what is f of 7x. So I go to this function, I replace all the x's with 7x's. So 4 times 7x plus 3 over 5 times 7x minus 8. And now when I multiply, 4 times 7, that's 28. So 28x plus 3. And on the bottom, 35x minus 8. Last one, and probably the most important one. F of x plus h. Now, the reason why this is an important one is because this is going to come up in calculus, all right? Not everyone here has to take calculus, but most of you do. So this being able to plug x plus h into a function is something that you're going to need to be good at. So let's just go here. Let's replace all of our x's with x plus h's. We're going to talk a little bit more about that today, why we're even interested in plugging x plus h into a function. So I replace the x's with x plus h. Because I have multiplication, I'm going to have to distribute the 4 through and the 5. And so that should give me 4x plus 4h plus 3. And then on the bottom, 5x plus 5h minus 8. And there's nothing else I can do. I just leave it like that. So everything in blue was me plugging in a variable expression and getting a variable expression out. Everything in red was me plugging a number in and getting a number out, right? Okay, so hopefully that example, along with the example we did before last class, hopefully those two together kind of remind you of how we evaluate functions. The next topic that we need to discuss, let me see here, I'm looking at my list of topics that I want to talk about. There we go. The next big idea now, and the thing that we need to know, is domains of functions. Now, last class, I talked about how I always like to think of a function as like a car wash. And I said, certain car washes, you can plug in any card, or sometimes you can't put an 18-wheeler through the car wash. So the domain of a function is basically what can be plugged in, right? What are you allowed to plug into a function? So let's start with a very simple example. Let's say I give you a function, f of x equals 3x plus 7. And then I ask you, what is the domain? I'm going to write dom f. And what that means is, what is the domain of this function? So what I'm asking you is, what values of x are okay to plug in here? So when you look at this function, you're thinking about, are there any numbers that when I plug them in, the function like freaks out and can't like get an answer for me? And so think about what would happen if I take a number, plug it in here. The first thing that happens to it is it gets multiplied by 3, right? Now you can multiply any number by 3. You're never going to have a problem, right? And then you're going to add 7. And you can always add 7 to any number. So there's no restriction on what I can plug in here. Now, as I do more examples, hopefully it'll start to become clear when you do have problems with the domain. Here we do not. There's no number that's going to cause a problem. So I need to somehow tell you that any value you want to plug in can be plugged in, all right? And there's multiple ways to say that. One way to say it is that the domain is all real numbers. You've probably seen that before. All real numbers, you could write that out. Another way that you could write all real numbers is to use what we call a double struct bar, capital R. That represents all real numbers. Another way you can say it is the set. So when we use a brace in math, it represents a set. So it's the set of all x's. Then you put a bar. That bar means such that and then you put x is bigger than negative infinity and less than infinity, and then close the brace out. So this is called set notation. I'm giving you these different notations because depending on what math class you're in, they might use different notations for representing sets of numbers. All real numbers, this means all real numbers. This means you are allowed to plug in any x such that the x is between negative infinity and infinity, which means it can be anything, right? Any number. And then one other way you could do it is to use what's called interval notation, where you just write down parenthesis, negative infinity, comma to infinity. And this is called interval notation. At the end of the day, though, what we're saying is that for this particular function, you can plug in any number and you're not going to have any problems. So these things aren't very interesting. Okay, functions that have a domain of all real numbers are pretty boring. We want to now look at some functions that do have problems. So let's start with this one. Well, for the next example. Okay, so the next one, let's do f of x is x over 4 minus 3x. All right, so for this particular function, I want to know what the domain is. And when I think about domain, I think about, I'm not like, in my mind, I don't sit there and ask myself, oh, for what values of x is this function good? I always ask myself, for what values of x is this function bad? So when am I ever going to have a problem? So when I look at this, I say, all right, look, I've got a fraction, right? Which means I have a denominator. And we know in our mathematical system, you can never divide by 0, right? You can't divide by 0. So what I'm going to do to figure out the domain is I'm going to ask myself that question. Look, this 4 minus 3x, that cannot be 0, right? It can't be 0, or else I have a problem. And then I'm going to treat this like a little linear equation, and I'm going to solve it. Now, I want to do it this way. I'm actually going to replace this not equals with equals. So what I'm doing right now, this first part is me saying, hey, look, I have a problem if this is equal to 0, right? So I do not want this equal to 0. The next line is me saying, oh, well, let me go see where it is 0. And then whatever I get, I'm going to throw that number or those numbers out. Those will not be part of my domain. So this is what I want. And this is going to actually help me figure out where that happens, you know? So for this is just a linear equation. I would just add 3x to both sides, and then I divide by 3. So if x is 4/3, I have a problem, right? I have a problem if x is 4/3. So how do I tell you that the domain is pretty much everything except this number, right? And there's multiple ways to do it. The way I'm going to do it, I'm going to show you both set and interval notation ways to do this, all right? So first I'm going to do set notation. So for this problem, the domain of this, I'm going to say set first. So it's the set of x such that, well, the only condition I have is that it can't be 4/3. So I'm just going to say x is not 4/3. So it's the set of all x's that have the condition that the number is just not 4/3. As long as it's not 4/3, you're in business. That makes sense to everyone? Now, that's the set notation. Interval notation, I always like to look at the interval notation. I always draw myself a number line. And then I put the point that we have a problem at 4/3. And since we do not want that point, I'm going to put an open circle there. And then I'm going to remember that it can be anything over here and anything over here, right? So any number to the left of 4/3, any number to the right of 4/3 would work. So written as an interval, let's see if anyone remembers how to do this. How would you represent all this stuff over here on the left-hand side in an interval notation? Does anyone know?
Yes.
Go ahead, Juan.
You would do negative infinity, comma 4/3,
Okay,
with parentheses.
on
Was-
both of these?
Yes.
Okay, good. That takes care of the left side. How about the right side?
You would do a U,
Okay,
Or-
U, yep. And
Parent-
then,
4/3, and to infinity.
okay, good. That is integral notation. Now, what it means is that you can pick any number between negative infinity and 4/3, anything to the left of 4/3. And then this U means union, meaning that there's a whole other set of numbers that you can pick. And that would be anything from 4/3 on to infinity. Now, something subtle but important here is the use of the parentheses. Anytime you use a parenthesis, that means that you can go all the way up to 4/3, as close as you want to get to 4/3, but you can't actually ever plug in 4/3. If you want to plug 4/3 in, you have to change that parenthesis to a bracket. So because I don't want to include 4/3, I stopped right there and put a parenthesis. Now, in terms of the infinities, you always put parenthesis on infinity, always, because infinity is an idea. Infinity is not a number. Okay, infinity is just this mental construction we have that it goes forever. So you can't put a bracket because that would mean you stop at some point, which you don't. All right, we good? I looked at it, said, oh, I can't have division by 0. Let me go figure out when I get division by 0, and let me throw that answer out. Yes? So we're always looking with functions, do we ever get division by 0, right? You think about that. Let me give you another one. What about the top being 0? Hold on. What if the top of this function was 0? Like, can I plug 0 in for x? Because that would give me 0 on top. Is that bad or no?
No.
No, it's not. You can have 0 on the top. You just can't have 0 on the bottom. Right? Why can't we divide by 0? I know you've all been told that, but why can't we?
Because the answer is undefined.
But why? Right? Like, I mean, that you've been told it's undefined, but why is it undefined?
Well,
It doesn't seem very satisfying.
There's nothing to define. There's no division.
Yeah. But how? I mean, like, if you're trying to explain to someone who's just learning about numbers, why are they told that, why, how can you explain that division by 0 is not allowed? I mean, I know we all know you can't do it, but what's the issue?
if you plug it into a long division equation, there's no number you can multiply it with that would ever make it equal something else.
Okay, so like, okay, I think what you're getting at is this. If I did 12 divided by, let's say 4, and then did like long division 12 here and 4 here, right? Then my task is to try and come up with a number that I multiply times 4 to get 12, right?
Yeah.
Which means 3, and that would work, yes?
Yeah.
So the answer to this is 3. Oops, 3. So you're saying if I did 12 divided by 0 and set it up the same way, 12, and then put 0 out here, then you have to figure out what number can I multiply times 0 to get 12, right?
Yes.
And that's just never going to happen, right? It's never going to happen. You're never going to be able to find a number to multiply by 0 and get 12. That's a good explanation. I like that, Josiah. That's good. Another way that I've seen it explained is that when we talk about fractions, like 1/4, 1/4, you could think of this visually as like a candy bar that's been cut into 4 equal pieces, right? And to say 1/4 means you're going to take one of those 4 pieces. If you take, let's say 4/1, flip it around, then what you're saying is I'm going to have a candy bar, and the denominator is how many pieces you cut it into, okay? So for this first candy bar, the 4 was how many equal pieces I had, and then I took one of them, right? Here, I take candy bar and I cut it into 1 piece. Well, it is 1 piece, isn't it? A candy bar by itself is just 1 piece, but I want 4 of them. So that means I'm going to take 4 candy bars. Right, so 4/1 is 4. 4 candy bars. 1/4 is 1 part. You take candy bar, cut it into 4 parts, take one of them. If I put 0 over 4, then I put a candy bar into 4 equal pieces and take how many of them?
None of them.
None of them. So how much do I have? Nothing, right? So 0 on top is not a problem. It's like cut it up and then take nothing. So you walk away empty-handed. This is where you have the problem. Because if you try to divide by 0, what you're saying is, okay, you have a candy bar, right? And make it into 0 pieces. Well, it already is 1 piece, right? I mean, a candy bar is 1 piece. So how can you make it 0 pieces? And if you want to say, okay, then there's no candy bar, then how in the world am I supposed to take four of them? I can't take 4 from nothing, right? So this is just doesn't make sense. This doesn't make sense, all right? I just don't want us to just, continue in our math lives and just be like, oh, well, they told me I couldn't do it. I want you to understand it's because our idea of multiplication division breaks down when we try and do it, right? Okay, here we go. Moving on, a new function. How about this? How about x plus 1 over x squared plus 4? So I want you all to look at that. The first thing you should see, oh, I want to know what the domain is, okay? The first thing that you should be thinking here is hey, I see a fraction, right? And as soon as you see a fraction, you should be thinking the denominator. I need to make sure the denominator is not 0. So you focus your attention here on the denominator and you say to yourself, hey, wait a minute, x squared plus 4x, I need to make sure that that's not 0, right? That's what I want, to make sure that's not 0. So now I ask myself, when is it 0, right? I'm going to go figure out when it is 0. And what do you say to that, everyone? Think about this problem. You have some number squared, and then you're going to add 4. Can that ever be 0?
No,
No, why?
because no number squared will ever equal a negative.
Yeah, so no matter what number you ever take, if you square a number, right, it's got to come out positive. The worst case scenario is that you plug 0 in, right? What if you square 0? You get 0, right? But you're going to add 4. Every time you're going to add 4. So no matter what, this can never be 0. Another way to see it is just move the 4 over to the other side, right? Some number squared can't be negative. Or you could take the square root on both sides here, and we don't do square roots and negatives, right? Not in this class. So what do we say here? This equation has what? No solutions, right? No solutions to this. Which means I do not need to worry about the denominator ever being 0, do I? It's never going to be 0. Is that the only problem we have here? Is that the only thing this function has as an issue? Division by 0, right? That's the only thing that could possibly go wrong here. So since it can never happen, my domain should be what?
Negative infinity to infinity.
Yeah.
Or all real
negative
numbers.
infinity, or all real numbers, however you want to say it. You can say it any of these ways up here. Let's take that same problem and let's change it slightly. Let's do x plus 1 over x squared minus 4. Right, so all I did was change the plus to a minus, that's it. Same question, domain of f. So now we do have an issue, because this right here, we want to make sure that that is not 0, right? That's what we want. So now I'm going to go figure out when it is. Now we've already talked about how to solve equations, right? Oops. I'm going to copy this to the next page because I'm out of room. So we've already talked about how to solve equations. There's so many different ways to solve that one. I'm just going to do a difference of squares just to practice it. And then this gives you two answers, -2 and 2. So we have two places where we're going to have a problem. If we try and plug 2 or -2 in, this function is going to fall apart because you'll have division by 0. So how do we say everything except those numbers? Well, in one way I could do it is this, x such that x is not equal to 2 and sorry, and x is not equal to 2. Any x you can think of, so long as it's not -2 and it's not +2. With the interval notation, again, I'll draw a picture. Here's -2, here's 2. I don't want those two values. I want everything over here, everything in between, everything this way. So there's actually like 3 little sets of numbers I need to include. So the way I'd write that is this piece would become -∞ to -2, not including -2. Then the piece in the middle would become -2 all the way to 2. And then this piece would become 2 out to infinity. And then we always just throw unions between them. Are there any questions on this? I'm not quite sure everyone's background with interval notation and set notation. All right.
Yeah, I have a question. Does it matter which way we write our answer at the end of the day or not really?
Like how you write your answer?
Yes.
So here's the thing, on the homework system, like the online homework system, it's going to probably dictate to you what it wants. If we ever wind up face to face again, I'm not going to care so long as your answer makes sense and is correct. All right. So I have not done the homework for this section online yet, so I have yet to see how they want the answers. When I'm doing the homework, you can watch my homework solution video. I'll probably talk about this during the video, like, oh crap, here's how they want it. And, we'll have to figure it out I'll have to figure it out as I go. But is that okay, Gregory? Understand?
Yes, thank you.
Yeah, I don't want the computer program to be an issue for us. That's one thing I don't like about online homework systems is that they're very picky about things. All right, we good?
So for clarification on something, the reason why this is so much more of an issue than the last one is because this has the -4 instead of the +4 on the denominator.
Absolutely. It is actually possible to make that denominator 0. There are 2 numbers that will make this 0 down here. Whereas in the previous one, no number will make it 0 because it was a plus between them.
Okay, thank you.
Mhm. Okay, let's do another one. All right, we have a square root, right? So what is the domain of this function? So what is the condition we have with square roots in this class? What can we not do?
You can't take the square root of a negative number.
Can't have a negative under a square root. Do we all agree with that? We all understand that? You cannot take the square root of a negative number. Can you take the cube root of a negative number? Cube root.
Yes.
Yes. Can you take the 4th root of a negative number? So let me write this down. If you do the square root of a negative number, no, right? If you do the cube root of a negative number, yes. If you do the 4th root of a negative number, no. You do the 5th root of a negative number, yes. So if it's an even root of a negative, you can't do it. An odd root of a negative, you can. So here we have a square root, right? So what we want to make sure, right? What we want is to be absolutely sure that whatever's underneath this root, which is technically called the radicand, we want to make sure that that is never negative, right? never negative. So really the opposite of that means we need it to be greater than or equal to 0. Right? That's what we need. That's what we want. We want to figure out what will make that radicand bigger than or equal to 0, which is basically the opposite of being negative. So in the previous problem, I'm going to highlight this in blue. Let me go back to the first thing we did. In the first problem I did, right, when we were looking at what was an issue, this thing that I set equal to 0, what type of equation is this? What type of equation is that?
Linear?
Linear, right? So when we were doing this problem, we had to solve a linear equation, which we all should be comfortable doing, move things around, solve for x. In the second problem, well, we set this equal to 0. This is a quadratic equation, isn't it? That had no solutions. And the next problem, we set the bottom equal to 0. We had a quadratic again, right? But that one had 2 solutions. Now what we're doing is looking at this. This has a name. This is not a linear equation. This is not a quadratic equation. This is what we call linear inequality. A linear inequality. And the way that you solve a linear inequality is exactly the same as the way you solve a linear equation, with one little exception. But let's see, let's just solve this. We move the 8 over, so we subtract 8 on both sides. And we divide both sides by 5. So for this function to be defined and not have problems, we need that the radicand was not negative or greater than or equal to 0. And that means at the end of solving this, that the x value we plug in has to be bigger than or equal to negative 8 fifths. So this should be our domain. So the way I'd write that is the set of x such that x is greater than or equal to negative 8 fifths. That would be interval notation. Number line would look like this. Here's negative 8 fifths. We need to be greater than it, everything this way, but we can also be equal to it, right? That's the little bar underneath. So I'll put a solid dot there. Anything out from here to the right. The way we write that in interval notation is to put negative 8 fifths to infinity, parenthesis on the infinity because it goes forever. But because we want to include negative 8 fifths, we put the bracket. This is the first time we've used the bracket. The bracket means included. Okay, so I'm trying to get you to see a couple of things here. When you're trying to solve domain problems, you're usually going to wind up with some sort of equation. We've had to solve a linear equation, quadratic equation, 2 quadratic equations, and now we've had to do a linear inequality. All right, a linear inequality. There's another kind of thing I want you to be able to see or handle. And this, in my calculus classes, this is the one that causes the biggest issue. This one right here. When a student gets something like this. I want the domain of this. So we have actually 2 different things happening right now simultaneously. We have a fraction, which means that the denominator can never be 0, but we also have a square root, and so we know that what goes underneath that square root can't be negative. So I want to highlight this right here. What do we want? What is it about that x squared minus 4 that I want to be true? Can it be 0? Can x squared minus 4x, can that be equal to 0? No? Why not, Carissa? If this is 0, Carissa, what?
Then we would have to be dividing by 0, which we can't
Yeah,
do.
we would have division by 0, right? Wouldn't we? That's no good. So we don't want this to ever be equal to 0.
We
We
also
also
can't,
don't want it, go ahead, Josiah.
we also can't have it be a negative, right? Because we can't
also-
radicalize negatives.
That's right. So we can't have it be negative or 0, which means it has to be strictly greater than 0, doesn't it? Strictly greater. So I'm going to say this must be greater than 0. See, we didn't have that in the previous problem. In the previous problem, it had to be greater than or equal to 0. It could be equal to 0 because the square root of 0 is 0. That's not a problem. The fact that we have a fraction now prevents this from being 0 because you have division by 0. So we have to be strictly greater than 0. And this is the thing that causes my calculus students problems. This is called a quadratic inequality. In quadratic inequalities, you have to be extremely careful in how you solve them. Right? The linear inequalities, you move things around kind of like you do with linear equations. Quadratic inequalities are extremely dangerous. And there's kind of a procedure that we use to figure out, to get the solutions. So here's the procedure. The first thing you do to solve a quadratic inequality is you will write down the quadratic as an equation first. Okay, so we're going to do it as an equation, not an inequality. We're going to replace this with equals. And just keep in mind what we're trying to figure out. We're trying to figure out when is this positive, right? When is it bigger than 0? So the first thing we're going to figure out is when is it 0? Okay, let's figure that out first. So I can factor GCF, greatest common factor, right? Pull an X out of both of those. Set each of those factors equal to 0. And we will get 2 solutions. Okay, we'll get 2 answers. Now, this is not our answer. This is how we do quadratic inequalities, all right? That's the first step. You figure out where it is 0. The next step is to draw a number line and put those 2 answers on the number line. When we do this, we are now what we've done is we've now taken the entire number line and we've broken it up into 3 regions. We have a region here, a region here, and a region here. And what we're going to do is try and figure out whether or not this thing in yellow is actually a positive number when we're over here, here, and here. So we have to check in each of the 3 regions what would happen to this yellow expression. So we have to pick what we call test points. I'm going to pick a test point here, -1. I'm going to pick a test point in here. Any number I want, just has to be between 0 and 4. And anything I want to the right of 4, so I'll pick 7. If you wanted to pick -10, 1, and 8, that would be fine. It's totally up to you. And you now have to check each of these into the yellow one. So let's plug the -1 in first. -1 squared minus 4 times -1. The question is that greater than 0? So if I take -1, plug it in here, is this true? So that becomes -1 squared is 1, and then -4 times -1, that's +4. Hey, wait, that works, right? 1 plus 4, that's bigger than 0. That means any number I would have picked, over here will work. All you have to do is check 1, but then you're guaranteed that everything over there will work. Then we have to do the same thing for 2 and for 7. So let's try 2. If you plug 2 in there, what happens? You get 4, take away 8, greater than 0, that's -4, greater than 0, and that's not true. -4 is not bigger than 0. So that means this doesn't work. Anything between 0 and 4 does not work. And finally, you plug in 7, which I'm not going to show, okay? You just have to trust me that it works. So let's get the answer then. Our answer is basically everything to the left of 0 and everything to the right of 4. Now, do we include 0 and 4? Do we include them or no? No, Juan's saying no. Why not? Why are we not including them? Aren't those numbers? Go ahead, Juan.
Because they're less than 0.
If we plug 0 in, right? If we plug 0 in here, we would get 0, wouldn't we? We would actually get 0. And we want to make sure we're bigger than 0, right? We have to be strictly greater than 0. So if you try and plug 0 or 4 into this, you actually get 0. We know that because of this, right? That's where we got the 0 and 4 from. So we do not want to include those. So we want to leave these as like open. Those are open holes. Sorry, that's really terrible. Do it with open hole out this way, open hole out this way, like that. So I'm going to write the answer in interval notation. My personal preference, at least through the calculus sequences, to do interval notation. So the way I'd write this answer is everything to the left of 0, so negative infinity to 0, parenthesis, union, and then 4 to infinity, like that. Just so you see why I said this is dangerous, let me show you what students will do with this that's wrong. I hate to show the wrong thing, but I think it's important in this case. I'll see students do this. They'll factor like this. Then what they'll do is make up their own rule and they'll say, okay, that means I just need x to be greater than 0. And then this one, they'll say, I need x minus 4 to be greater than 0. And they'll create two little inequalities from this. And then what they do is they say, oh, x must be greater than 4. And then over here, x must be greater than 0. And that's what they say the answer is. And if you look at that on a number line, here's 0, here's 4. The first part here, greater than 0, means everything from here to the right. And then the second answer, x greater than 4, means everything from here to the right. So basically, you're saying that everything bigger than 0 works. But I already know 2 doesn't work, right? So there's a problem here. And the problem is you didn't do it right. That's not the way we solve quadratic inequalities. I know it's a pain in the butt to do this, but that's what's necessary to solve a quadratic inequality. There is another way. I'll just show it to you because I know some of you are pretty sharp here. The way that I do it is this. I mean, yes, I can do this, but the way I think about it is this. I look at this right here as a quadratic. And this requires that you have learned this in the past. That quadratic, when you graph it as a parabola and it opens up. I know it opens up because there's a 1 in front of x squared. If you don't know what I'm talking about, just ignore me. But it opens up. And by setting it equal to 0, I'm finding the x-intercepts. So those 2 points, 0 and 4 x-intercepts. And since the parabola opens up, I know that the parabola would have to look like this. And if I want to know when it's greater than 0, I'm just looking where the function is above the x-axis, which would be over here and over here. So I don't have to do any test points if I just know the shape of the graph. But again, that's if you already are familiar with parabolas and things like that. So, okay, we good? We good? All right, so you will have on your homework questions where you're asked to find the domain of some functions, all right? And that's basically what we're doing. So I'm trying, I told you I haven't taught this class in a long time. And the thing that's hard about it, there's two things that are hard for me. First of all, we're on Zoom. It's hard to manage the time properly in Zoom. It's just really difficult. I don't know why. It's just whenever I'm in a face-to-face class, we just seem to move in a different speed. That's one thing. The other thing is, what was I going to say? I lost it. I was thinking about something else. The time, because I haven't taught this class in a long time, it's hard for me to even know the correct speed to work through this material. Like if this were a calculus 2 class, like I've done that class for probably every semester for 20 years. So like, I know the speed, I know what we need to get through. I feel myself already falling behind here, but there's so much I want to say to you all. You know, there's like things I want to share with you about math and just, you know, so I'm trying to keep myself on track, but I think it's worth it. I'm doing that because I'm prefacing what I want to show you right now. We're going to lose some time, but I think it's important. I find it valuable. Why is it that we are not going to be looking at the square root of -4? I mean, I know some of you have learned in the past that this is basically going to be like 2i, this imaginary number. Like, why are we not doing it? Why are we not actually exploring imaginary numbers? I know you've seen them before. Maybe some of you have seen imaginary numbers, but why are we just kind of like not doing them? And I can tell you right now that in calculus, right, this is the calculus book we use, the entire subject of calculus that we study, Cal 1, 2, and 3, we never use imaginary numbers, ever. Okay, we stay far away from them. And there's a reason why. And that's what I want to take a moment to kind of explain to you. And it's tied into this class, so I think you can appreciate it. Think about this. When we have defined a function, right, which is what we're talking about today and yesterday or last class, basically we take numbers in and we spit numbers out, right? Number in, number out. Now, we can look at a function like this, or we can graph the functions, which is the next section we're going to talk about. When you graph a function, what you do is, let me give you a specific example. Let's say we took 2x plus 1. If I ask you to plug in 2 to this, you plug 2 in, you should get 5. And so a way to visualize that is to go on the x-axis 2 and go up 1, 2, 3, 4, 5, right? And you get a point. And if you put all the different solutions together, you know, plug in 3, you get 6. If you plot that point, you put them all on there, you will get the graph of this function, which would be a line. Okay, that graph is a visual way of understanding that function. Okay, so the graph is a visualization of what the function is doing. The reason we do not explore imaginary numbers is because in order for me to draw you an imaginary number, I need 2 dimensions. So what do I mean by that? If I ask you to right now to show me the number 4, everyone would just draw a number line. Here's 0, there's 4, you put a dot, there's 4, right? But if I give you an imaginary number, that's an example of what we call a complex number. In order for you to visualize that, you actually need 2 dimensions to do it. So if I plot that, it would look like this. It would be about right here. Okay, that's where that imaginary number lives. It lives in 2-dimensional space. So if I'm going to talk about functions, right? A function that takes a number to a number, like we've been doing, and then I have a graph. The graph, the input is the x-axis and the output is the y-axis. So 1 dimension for the input, 1 dimension for the output. Does that make sense? Like in this picture, the input is represented by the x-axis and the output is represented by the y. Your input is a number, so that's 1-dimensional. Your output is a number, that's 1-dimensional. If you try and talk about complex numbers, you're going to need 2 dimensions for the input and another 2 dimensions for the output, which means a graph would need how many dimensions?
4.
4. And what's the problem with that? Good luck. Draw me 4 dimensions on a flat sheet of paper. Okay, you're not going to do it. All right, it's not possible. We live in 3-dimensional space, right? We live in 3-dimensional space. You could say that time is a 4th dimension. We could start doing it, but it's so hard to understand what a function does if you allow imaginary numbers in. It's so hard to visualize what's going on that you have to have taken calculus 1, 2, 3, linear algebra, right? You need to have taken all these courses. In fact, I mean, you have to take a lot more math before they even let you in the door to a class that has complex numbers, because you're not going to be able to visualize it. So you have to be at a very high level mathematically, like your mental capacity in math has to be very high, because you're not going to be able to see it. It's all going to be like not imaginary, but it's going to be not easy to visualize. Okay, so that is why I just want you to know, like when you learn about imaginary numbers, right? Square root of -4 is I, or 2i, right? They tell you that. I've always thought that this is kind of crap because it's kind of like just opening the window saying, hey, look in there. You see that I? Okay, and then they close the window. You don't see it again for like way down the road if you're a math major. Okay, there's a reason why we don't do it. It's because we can't visualize it. Okay, that's my little spiel. Let's keep going. Any questions on that? All right. So we now need to talk about combinations of functions, or what are called the arithmetic operations on functions. All right. So when you're in grade school, you're learning about numbers. You're taught to add, subtract, multiply, divide, right? Those are the 4 arithmetic operations. Add, subtract, multiply, divide. Then you start learning about functions, and then you are told that you can actually add 2 functions, subtract 2 functions, multiply 2 functions, and divide 2 functions. That you have the same 4 arithmetic operations between functions. So I need some way of communicating to you. If I want you to take 2 functions and add them together, I need to somehow have a notation that lets you know to do that. So here's the notation. If we want to add 2 functions, then what we'll write is f plus g, and then in parentheses x. And what this means is you will take the f function and simply add it to the g function. So look, everyone, this is purely just a notation idea. It's how I communicate to you that I want you to do something with 2 functions. If I want you to add them, I'm going to tell you, I'm going to write this down. And all you do is add them up. If I want you to subtract 2 functions, I'm going to write f minus g and then parentheses x, and that means you just subtract them. Now remember though, with subtraction, order is important, right? 5 minus 4 is not 4 minus 5. So f minus g is not the same as g minus f. Addition is okay. Addition commutes. It doesn't matter what order you do them in. Okay, multiplication. If I want you to do multiplication, I will write f and then g right next to it with nothing between them. And so if you see fg, that means you multiply the 2 functions together. And finally, if I want you to divide, then I'll write f on top of g with the x, and that just means take the f function, divide the g function. All right, let's do an example. I'm going to give you 2 functions. So you're given that f of x is, let's start simple, 2x plus 3. And let's say that g of x is 4x minus 5. Find the following. All of these, okay? I want us to find all of these right here. Okay, and there's one more thing. And the domain of each. Don't forget the domain. All right, so let's start with the first one here. I'll do them in red so you can tell where my answer is. If I want to take f and add g together, all that means is write the f function down, add to it the g function written down, And that's it, just add them, collect like terms. So what would you get here? I haven't called on anyone today. I've been talking a lot. I apologize, but we have a lot to do. So let me call on someone. Is Lorena here?
Yeah.
All right, Lorena. Okay, so what would that be? You combine like terms, we get.
You get 6x
Okay, and then what else?
minus 2.
-2, yeah, okay. I didn't know if you knew you were muted still. Okay, now, Lorena, look at that. Do you have any domain issues with this? And so when I think domain, I think, do I ever see division or do I see square roots? So do you see any division or square roots here?
Division?
You see
Or
something divided here?
Oh, no, sorry.
No, right? If that X was in the bottom, we'd have an issue, right? So we should have no issues with the domain here, right? So the domain should be all real numbers. I'm just going to put that right here. Okay, is Megan here? Pretty sure Megan's not here. How about Hugo? Hugo? No? Amanda Martin?
Yes, sir. I'm here.
Okay, all right, good. How about the next one, F minus G? So tell me what I should write here.
Okay, so you're gonna take 2x plus 3
Okay,
minus 4x minus 5.
okay. Now with that subtraction, am I gonna need to be careful here? Because I'm supposed to be subtracting all of G, right? So if you put
Yes.
this minus here, that minus has to affect the entire G function. So we need this in parentheses, understand?
Yes, sir.
Okay,
It's not a negative 4x, it's a subtraction.
yep, it's gonna be minus 4x and then the minus hits the 5 also. So we'll write that on the next line, 2x plus 3, then minus 4x plus 5. See, if you don't put the parentheses, then it's gonna be off because you would have had a minus 5 here. Everyone see that? All right, Amanda, what do you get there if you put all that together?
Um, 6x,
Careful, 2x, you're
Oh.
taking away 4x.
so it would be negative 6, X.
Negative 2.
negative 2.
Just think about it like money, right? You have $2, take away $4, you'll have negative $2, right?
Yes,
And then you have the 3 and the 5, right?
yes, 8.
Do
Plus
do you see any domain issues here? Division by 0, I mean, do you have any division or square roots?
It's a negative 2x.
Okay, but is it division though? Do you have like anything in the denominator that could cause division by 0? Don't overthink it. I mean, do you see anything where you have on the bottom something that has x's in it?
No.
No, right? It's just negative 2x plus 8, right? It's a nice little line. It's basically a linear function. So this should have no issues. Our domain should be all real numbers. Okay, let's see here. Gloria, are you here? Gloria? No, Gloria. All right. Lizana? Lizana, are you here?
Yes.
Okay, so Lizana, how is this going, Lizana?
Okay, I'm going a little bit slower than you, but I think
Okay, yeah, I understand.
yeah.
So on this third one, Lizana, the F and the G together mean multiplication.
Mhm.
Right, so we want to take these two functions and multiply them. That means I want 2x plus 3, and I want to multiply it times the 4x minus 5. So very important that they're both in parentheses.
Mhm.
That way we can FOIL. All right, so I'm going to FOIL this out. Here, multiply this out. And let me see, I'm going to get 2x and 4x, that's 8x squared. 2x and -5 gives me -10x. And then we'll have plus 12x. And then finally -15. Lizana, do you feel like if I gave you enough time, you'd be okay with that? Multiplying that all out? Yeah.
Yeah.
And then collecting like terms together, the middle two terms come together to give you 2x -15. So that is the product of the two functions.
Mm,
Are there any domain issues there, Lizana, that you see? Do you see division by 0 or square root?
No.
Mm-mm. So it should be all real numbers. Good. All right, Christopher Mora, you here? Cecilia?
Yes.
Yes. How's it going, Cecilia?
Good.
Good, right? Okay, so what does this mean? F over G means I need to do what?
You need to divide them.
Divide. Okay, so you're just gonna take the F function, which is the 2x plus 3, right? And divide by the G function, 4x minus 5, right? That pretty straightforward to you?
Yes.
Okay, so that's it. I mean, we're done. That's the function. The tricky part's the domain. Because now you actually have a fraction, right, Cecilia?
Yeah.
And we got to make sure what? What is it that we need to make sure here? That what is not what?
That the denominator isn't
Isn't
0.
0. Okay, so I'm going to write that down. I want to make sure that 4x minus 5 can't be 0, right? And so what I do is I go figure out where it is, 0. So I'll trust that everyone can solve that. Just move the 5 over, divide by 4. So this value of x causes a problem. That causes a problem. So I want to remove this point from the domain. So the way I'm going to do that, I'm not going to draw the number line. I'm just going to go straight to the set note, interval notation. So this basically represents everything except 5/4. Everything except 5/4. Okay, so in your homework, you will have problems like this, all right? I think they're gonna be a little bit, some of them are gonna be a little bit more challenging because the functions are a little more challenging, but I just wanna see how you do with it. And remember, I'll try and post the solutions to that. Yeah, some of these are gonna be nasty, but I'll work through them myself too and see how, we'll see how it goes. All right, we're moving on. All doing all right? Let's take a poll. Oh, someone sent a chat. Oh. That must have been a while back. Let's take a quick poll. I'm just curious here. So choice 1 is yes, you do want to go back on campus and continue this class face-to-face. Choice 2 is, you know what, this Zoom will work. I'm okay with Zoom. Yeah, just curious to see what you would prefer. Okay, I think I shared the results there. So about 70% of you would like to get this thing face-to-face. And a few of you are like, okay, you know, this is good. Just curious. I don't have any control over that. I'm going to do what the college tells me to do. So, all right. So we're going to move on to a new topic. All right. And this topic, I remember when I was learning it as a student, it didn't make a whole hell of a lot of sense what we were doing, why we were doing it, why it was important. All right. So I think I know what I'd like to do is to show you where it is going to be used, all right, later. And I think I told you already that this class is about me teaching you how to use tools. Later on, you go build something with them, right? So I want to actually show you where this appears in calculus, all right? And then you'll see its value later, and then understand that all we're doing right here is just making sure we are proficient at the actual, like with using the tool. So let me take a moment to bring my notes up here from calculus. My notes are a little bit different for calculus. Where the heck is it? Okay, here it is. Okay, so I want you to imagine that we have just some arbitrary function sitting here, right? Just a graph of some function. And what I'm going to do is I'm going to pick some point on that graph. There it is, right? And then I'm going to pick a second point on that graph somewhere else, right? So 2 points on the graph. And then I'm going to connect them with a straight line. There it is. We can always find the equation of a line that goes through 2 points. If someone gives us 2 points, we have a formula to find the equation of the line that goes through them. And what you need is to first know what the slope is. So we can look at this as being the rise and this as being the run. You've probably heard this before. And so the slope of this line, we call it M, is rise over run. That look familiar to you all? That look familiar? Okay. Now, let's just say, for the sake of me trying to make this make sense, let's say we call this point X, all right? Then this point right here would be the point X. That's what I'm plugging in, X, right? And then the Y value is whatever comes out of the function at X. So this Y coordinate would be f of X. Go with me? This point written as an ordered pair, X, f of X, that represents this point, yes? Yeah, no questions? Now I'm gonna pick that other point over here. I'm gonna do a different color. And that point is some other point. It's not X, right? I'm going to call it X plus something. So just think of it this way. If this was, let's say, let's just say it was 5, this would be bigger than 5, right? So it'd be 5 plus something. It's just to the right of it. That's all that matters. Then this point up here would have as its X coordinate X plus H. And as its Y coordinate, it would have whatever you get when you plug X plus H into the function, right? Whatever this is, it's X plus H, whatever it is, you plug it into the function and spits out f of X plus H. Does that look familiar, f of X plus H? Didn't I put stars next to that a little while ago and said this is important later? This is why, this is where it comes from. So we have 2 arbitrary points, right? 2 arbitrary points. The slope of the line between those 2 points is your Y coordinate subtracted. Let me write the formula down first. Maybe when I write it, you'll recognize it. Do I remember seeing a formula like that? It's the difference of the Y coordinates divided by the difference of the X coordinates. That's your slope, rise over run. Which is, in this case, the difference of our Y coordinates. This is one of the Y coordinates, right? So let's put that here. We subtract from that the other Y coordinate, which is f of X. And we divide this whole thing by the difference of the X coordinates, which will be this one minus this one, like that. which gives us, let me clean this up just a little bit more. When I do the bottom, when I do x plus h minus x, the x's cancel, and all I'm left with is h. This right here is extremely important because that gives you the slope, right? That formula gives you the slope of the line connecting those 2 points on that function. That makes sense, everyone? Just, you don't need, I'm not going to test you on this. I just wanted you to see that that thing in the box represents the slope of a line connecting 2 points on some function. Okay? Yes? Yeah. Okay. Now, in calculus, here's what we do. We take that second point and we slide it over, slide it over, slide it over, and we put it right on top of the other point. And when you put it right on top of the other point, we have a problem. Because as soon as the points are the same points, you no longer have a change in y and a change in x. It's the same x coordinate, same y coordinate. So what you wind up getting is division by 0. And that's a major problem. Major problem. So we have a way around it, and that's what calculus is about. We do this thing called the limit, and we will have a way of addressing it. But before you can even do that in calculus, you have to be able to handle this idea right here. You have to be able to handle this thing. Algebraically, you need to be able to be very good at coming up with that little box. And it's so important in calculus that we have a special name for it. It's called the difference quotient. All right. And so what I'm going to do now for the rest of this class, 20 minutes I have left, I'm going to give you functions and we are going to practice doing the difference quotient on those functions. All right. So I hope that in some way helps you understand that I'm just not throwing some crazy thing at you just out of the blue here. There's a reason for it later. And let's start with this one. Because these problems will just look like they came out of the blue here if I don't like somehow support it with that picture. So here's the problem. Find the difference quotient. Okay, so find the difference quotient of f. That is, do this. That's what I just showed you, right? That's the formula I just showed you. They want us to do that for this function. So I always like to think of the difference quotient as having 3 parts to it. It has a top left part that's in blue. Let me erase all that. The top left part's in blue. We have to figure out what that is. We have to figure out the top right part in green and then subtract those two. And then the bottom in the difference quotient will always be h. Okay, it's always going to be h. So you just have to figure out what 3 things are and we will have the difference quotient. The thing is, the difference quotient is something different for each function. So like, if I give you a different function, the difference quotient is going to turn out to be a different answer, right? So this is like a generic formula. I have to provide you the function now, and then you do the difference quotient. So here's the function, and let's find the different parts. So I like to kind of, at least while we're starting, I'm going to just kind of do the parts on the side. First thing I want is f of x plus h. Okay, so what I'm doing right now is I'm going to go try and figure out what that top left of this thing is. Now that's a problem that I started class with, isn't it? I ask you to plug x plus h into a function. Here's the function, which means I replace all the x's with x plus h's. Right? That's what it means to plug x plus h into the function. Now we still have algebra to do here. I am going to square this. Okay, I'm going to square this. But we spent last class talking about that also, right? I did Pascal's triangle for you and stuff, told you there's a way to do this. I expect that everyone in here could FOIL that out and get to this answer on your own. Okay, so if you FOIL this, you should get x squared plus 2xh plus h squared. Then you will have to distribute the -2 through the parentheses. So that'll give you -2x minus 2h. And then you'll always have that +2 on the outside back here. Now that is just the top left corner of the difference quotient, right? That's just the part in blue. Are there any questions on that? Can we combine any of these things together? These things, are there any like terms? Can we put anything together or no?
No.
No, right? There's no like terms. So that's it. That is the top left corner. Now, the next thing I'm going to do is figure out the green part. Now, guess what? The green part's the easiest one because it's just f of x, right? And f of x is exactly the function, the way it's written, x squared minus 2x plus 2, right? So now I've got the top left and the top right. Okay, maybe the bottom's the easiest. H is always just h. So we're ready now to just put it all together. Okay, just put it all together now into one final expression. So here's the difference quotient. I'm going to write DQ, not for Dairy Queen. Difference quotient should be equal to the blue part, which we said was x squared plus 2xh plus h squared minus 2x minus 2h plus 2. That's the blue. I'm going to move this over a little bit. Okay, now looking at the formula, I now need to subtract, right? I need to subtract from that, subtract f of x. Now f of x is this, right? But again, because we're subtracting, I must put that in parentheses. Okay, so that's this green part, f of x. And then the whole thing divided by h. So I have set the difference quotient up. Everything's in place. And now you have to simplify this. I think this is one of the hardest parts right here. This part, you have to simplify. So watch what I do. I'm going to distribute the negative through. That looks very complicated, doesn't it? It looks like a mess. But a lot of good stuff is about to happen. You should get a bunch of things to cancel. X squared minus x squared. 2x, negative 2x, and positive 2x. Positive 2 and negative 2. Those all go away. Right? And then the only thing we have left is 2xh plus h squared minus 2h over h. Almost there. Notice in the numerator that every term has an h in it, which means I can pull a GCF out of the top. Right, pull one factor of h out of each of these, and then I can reduce that out, and we are left with a final answer of 2x plus h minus 2. Now, that's going to be the answer, and you're going to be like, well, what does this mean? What is it? You know, what are we going to use this for? Like I said, in a calculus class, we would then continue doing something else, okay? But you have to be able to do this mechanical part of it first. So you just have to kind of like, this is our answer, but you know, if you really want to know, you know, stay tuned. take calculus, all right? All right, now this was an actual easy problem because it was just a polynomial. We have 15 minutes. I'd like to throw a problem at you now that is going to be much more difficult. The algebra is going to be much more difficult. And I want to try and maybe put y'all in groups. Let me say one thing. Do you see at the end of the problem, that we got the h's to cancel? Okay. In all the difference quotient problems that you are going to be presented with in this class, okay, and everything you're presented with, you should get that h to cancel. If you can't get this h to cancel, you've done something wrong, all right? Something is off. All right, so I'm trying to think, how bad do I want to throw you into the fire here? Man. Yeah, let me just throw you into the fire. I mean, it's the next problem on the homework, so let me go with it. So I want you to find the difference quotient. In other words, I want you to find f of x plus h minus f of x all over h for the function f of x equals 6x over x plus 2. Okay, this is going to not be that great. It's going to suck. Let's do this. Let's not do groups. Let's not do groups. Let's just stay where we are and do this. At the very minimum, what I want you to do is at least get this set up. Okay, meaning at least try and figure out what the top left corner is, then go figure out what the top right corner is. Of course, the bottom will always be h. Put all the pieces together into an expression. And then if you can do that, go ahead and try and do some algebra on it. But if you can at least get the difference quotient set up, that'll be progress at this point. All right. So let's take some time, and we'll probably take about 6 minutes or so, 7 minutes, just to see if you can get it set up. If you have a question, please just, say something. I'll be happy to answer. I'm checking my email right now to see if there's any updates on what's going on next week. I'm gonna start working this out, but I'm gonna do it in silence and you can kind of look up and see if you're getting the same thing. Hopefully you were able to get what I have written there. Does anybody have any questions on what I have here? Plugging in x plus h for x here and here. This is all good. Distribute the 6 through, so there's no issues. Here's where we are. Now, like I said, if you do this right, you should be able to get this h to cancel. Should be able to. But it's not obvious from here how this h is going to go away. So what we're going to need to do is try and combine these two fractions into one fraction, these two. And it's going to be messy because that means we need a common denominator between these two. And that means I have to multiply the first fraction by the other denominator. And then I have to multiply this fraction by the other one's denominator. Do y'all understand what I'm doing? If you want to put two fractions together, you have to have the same denominator. So that's what I have to do. I have to introduce that. And that's going to get very messy. All right, as we're about to see. So here we go. I've got about 6 minutes. So let me just go ahead and do this. When I multiply this top left right here, I have to do a little FOIL here. So I get 6x squared. I get plus 6xh. Then the middle terms, plus 12x. Then the last terms, plus 12h. Now, all of that is over the common denominator, which I'm not going to multiply out. All right, I'm just going to leave this as the x plus 2 times the x plus h plus 2. Okay, so all I've done here, this right here is this. Any questions on that step? Have to subtract from that these multiplied. So I'll pass this 6x through here. So I'm going to subtract from that the 6x squared minus, plus 6xh, and then plus 12x. And then all of that is divided by the common denominator. And all of that is divided by h. It's messy, huh? It's messy. Now, these two have the same denominator, so we can put them together, but be real careful with that minus sign. That minus sign right there has to distribute across the top of this one. So we'll have 6x squared plus 6xh plus 12x plus 12h. Now here comes the minus stuff. Minus 6x squared minus 6xh minus 12x. All of that is now on top of the common denominator. But all of that is on top of h. And so now we can start canceling things out. We get some good stuff going on here. This 6x squared cancels out with that one. What else goes away?
Positive.
6xh.
The 12x, okay, that goes away. Oh, I also heard 6xh goes away. It's a lot of stuff that went away, didn't it? All we're left with is 12h on top. It's the only thing I see. So we have 12h over the common denominator below that. But then all of that is on top of h. And now, because that h and that h are there, we can just cancel them out. Now, if you're unsure of how that works, just so I'm clear, you can look at this as a fraction over a fraction, like this fraction on top of this fraction. And then remember, division is the same as multiplication of the reciprocal. So dividing this thing by h over 1 is the same as multiplying by 1 over h. And maybe that's a little easier for you to see that those h's would cancel. Either way, they're gone. Okay, so you get the 12 on top, and on the bottom, you get the x plus 2 times x plus h plus 2. And that
Can we FOIL the denominator or no?
you can. It would not be wrong to multiply this out, but it's not necessary. And actually, in a calculus class, you would not. You just leave it, because what we would do the next step, you actually wouldn't want it multiplied out. It would be easier to leave it not multiplied. The only thing you had to multiply out was up here. When you combine these two together, you had to multiply out the numerators, because that's where you get all this canceling from. Okay, so what I'd like for you to do, okay, is attempt the homework for this section. All right, go ahead and try and do the homework for functions, domain, difference quotient online. Do that homework set. I'm going to try and get that video up for that in the next day or two. All right, but please try and have that done by the next time that we meet, which will be technically next Wednesday. I don't know where. It's either going to be on Zoom or on campus, but yeah, that's it. So 3.1 is the only thing I want you to be working on for over the weekend. Any questions? Okay, everybody have a great weekend. Labor Day, right? Is it Labor Day? What's the holiday? I don't even know.
Labor Day.
Labor Day? Okay. Yeah, so have a good weekend, and keep yourself posted on Canvas. You know, keep checking to make sure. I'm sure they're going to send something out to everyone at some point. So, okay, have a good one. I'll hang out here if you have a question.
Have a good weekend.
Thank you.
Bye. Have a good weekend.
Thank you, Professor.